Problem 18.43. The marketing manager of a branch office of a telephone company wants to study characteristics of residential customers served by her office. In particular, she wants to estimate the mean monthly cost of calls within the local calling region. In order to determine the sample size necessary, she needs an estimate of the standard deviation. Okay, so in terms of our background information, ultimately we're wanting to study mean monthly call costs, but to do that we need to do a proper survey, and to decide how big that survey should be we need to firstly come up with an estimate of the standard deviation. So a little bit of background information there. The key thing with this question is to read it very carefully and to realize that our first step in the analysis is to estimate the standard deviation. So now if we have a look at part A, on the basis of her past experience and judgment, she estimates that the standard deviation is equal to $12. So that's her starting point. Suppose that a small-scale study of 15 residential customers indicates a sample standard deviation of $9.25. At the 10% level of significance, is there evidence that the population standard deviation is different from $12? So if you're in any doubt from the background information, part A clearly states that we're wanting to test out a claim in relation to the population standard deviation being $12. We're starting off with that as an estimate, and then we're just using a small scale study of size 15 to come up with our sample evidence. Now the sample standard deviation is a little bit less than $12, but of course that could be just natural sampling variation, or it could be that the population standard deviation isn't $12. So that's what we can look at with our hypothesis test. Now as soon as we see that 10% level of significance, we know it's definitely a hypothesis test that we're going to complete, and we're looking in particular to see if our evidence shows that the population standard deviation is different from $12. So that different keyword is very important, because that's how we know that we're specifically going to implement a two-tail test. So if we jump in and start setting everything up, we've got that the null, remember, always involves equals, so that is sigma, our population standard deviation, equal to 12. Because we're wanting to see if the evidence shows that it's different from $12, our alternative is then the complement, sigma not equal to $12. So it's a two-tailed test. Our alpha is 10%, which is 0.1 as a decimal, and we can then go to setting up our decision diagram. Now a one population test for standard deviation or variance is a chi-squared distribution. So I draw up my decision diagram. It's a chi-squared diagram, and I know for the chi-squared distribution I must have degrees of freedom. Now in this particular application, degrees of freedom will be n minus 1, which in this case, remember, it was a small study of 15 customers, so our degrees of freedom is just 15 minus 1, which is equal to 14. From there I can go to the 14 degrees of freedom row in my chi-squared table. Now it's a two-tailed test, so our alpha of 10% is broken up into an upper tail reject region and a lower tail reject region, each of 5% in size, so 0.05 as a decimal. Now if I go to row 14 in my chi-squared distribution and look up an upper tail 5%, I get a cutoff of 23.685. So that's the cutoff for the upper tail reject region. Now the trick with the chi-squared distribution, when it is a two-tailed test, when we go to find the lower reject region cutoff point, notice we know that below that point we have 5% of the distribution. Now the trick with the chi-squared tables is that they only work on the basis of an upper tail area. So when I want to find that lower cutoff, well, yes, there's 5% below, but in terms of what I've got to look up in row 14 of the chi-squared table, I've got to say, well, if there's 5% below that point, how much is above? How much is in the upper tail for that particular cutoff? 5% below means 95% above. If I look up the column that represents an upper tail of 95%, the cutoff is 6.571. So a little bit of a trick when we're getting a two-tail decision diagram for a chi-squared distribution. You can look up the upper tail reject region cutoff directly, but you've just got to think a little bit more to get the lower tail cutoff. So having now completed our decision diagram, we can just remind ourselves that, okay, the sample size was 15, sample standard deviation S was $9.25. So that allows us to now complete the test statistic. It's not too bad to work out for this test. It's just n minus 1 times sample variance divided by population variance. We can substitute everything in. We've got sample standard deviation S, so we just square that. That's the $9.25 squared. Now in terms of sigma, well, remember when you do a hypothesis test, you work on the assumption that the null is true. If the null is true, sigma is $12, so we can substitute that in. Put that all into your calculator and we come up with 8.319 as our test statistic. Now we can then compare that to our decision diagram and we can see that it's clearly within the non-reject region. So our initial decision is to not reject the null, and if we then turn that into a sentence relating to the alternative hypothesis, we can say there is not sufficient evidence to conclude that the standard deviation of the monthly cost of calls within the local calling region differs from $12. So you could have said there's not sufficient evidence that it's different from $12, that there's not sufficient evidence that it's not equal to $12. Either wording would be fine. So what we're seeing basically is that even though our sample standard deviation is less than the hypothesized standard deviation, it's not far enough away for us to reject the null. We're thinking that the difference is just natural sampling variation. Now we had a part B to this question. What assumption do you need to make in order to perform this test? Well, it's a fairly straightforward assumption. We're just assuming that the data in the population are normally distributed.